Good morning, Calculus 2 students. I think you all have the distinct advantage of having a class that wakes you up at the beginning of the week. I guess you have to look at it as an advantage. I've gone ahead and made a announcement about the next test. It's just like the last test. The window of time will be the same. And I encourage you to take advantage of study time, either to do additional practice for the test or go ahead and get caught up with some of the new material that we're covering, especially with the trig substitution. And what we'll talk about today will be the partial fraction decomposition. The trig sub is lengthy, but not difficult. The partial fractions, again, you won't find to be very difficult, but just lots of steps. And as you found out in pre-cal, the problems that you do now take lots of steps as opposed to one or two. And so you have to be a lot more vigilant about your work. So what I wanted to do first, before we start into the partial fractions, is just to do an arc length calculation. That is, lots of times when we were doing the arc length computations back at the beginning of the class, we found that lots of the algebra and all was a little bit different. That is, we had really interesting functions, basically so that we could actually do the integral, because we didn't have other more elaborate integrating techniques. So the particular functions had to be set up in a way that you would actually get an integrand that you knew how to deal with. And so what we did at the time was to avoid some simpler curves that you may have thought at the time would be the best candidates for arc length. And what we found is that even simple curves like quadratic functions are very difficult when it comes to computing arc length, because the integrals are more elaborate. Now, another curve, I thought this was a good example that I found in your textbook that basically discusses a curve that you talk about at length in college algebra and pre-cal, and that's the natural logarithm. So what we wanted to do in this particular case is to take the natural logarithm on the set 1 to 3 and compute the arc length. So what we want to do is compute, and I'll just write it out, compute the length of the curve. Now, when you think about this, just like before, you go back to the routine that we had with the mean value theorem, and this also reminds you of surface area. We use the frustum and the arc length element to get an area of computation. So this is basically a blast from the past. So like I'll say, as we learn new integration techniques, maybe we'll throw in some of these. And you are certainly welcome to always look for problems that keep your integrating techniques nice and sharp. So first, let's just go ahead and look at y prime. This is a good review. We just get 1 over x, the derivative of the natural log. And then what we want to do is write 1 plus y prime squared. So as you're preparing for the test, as you work through some of the new material, that's going to make you better at the old material. So keep that in mind. So this will give us 1 plus 1 over x squared. Now the integral we're going to get is going to be similar to one we've already done, but there'll be a difference of a minus sign. So now we get a common denominator because we need to do a square root. And of course, we're in the interval 1 to 3, so that'll help us with the absolute values. So now when we look at this, we can easily take the square root. So this implies that the square root of 1 plus y prime squared will just be the square root of this expression. So again, we just have to follow the rules so much of math is following rules and being consistent. And so now, of course, this will give us the square root of x squared plus 1. And then downstairs, of course, we get the absolute value of x. We certainly tire of the absolute value, but it is in our lives to stay. And then, of course, for this particular interval, we have x as the absolute value. So now what we remember is last week when I did a trig sub, I had a minus sign here. So we still use trig sub, but you can see this is very similar to a problem that I did in lecture. And so now we're thinking the tangent substitution because we have the x squared plus 1. The a is 1, so we have a very simple setup here. So now we'll do trig sub. Well, I'll write the integral, but obviously we're going to have to do trig sub. And forgive me for not saying trigonometric substitution. I know this is a little bit pedestrian, but we'll get over it, just maybe just to make life a little easier. So now the arc length, little s, will be the integral from 1 to 3 of the square root of x squared plus 1 divided by x dx. So now what you're thinking is that, okay, this is going to be one of those where we have to figure out the new limits and then switch the limits since we've got a definite integral. So this will be a little bit different from what we've done, but still good practice. So now x is just tangent theta. Again, we have the a is 1. So the dx will just be secant squared theta d theta. And then, of course, the x squared plus 1, we always write this out. You don't have to write all these steps out, but it just gives you a little added confidence. This will just be, in this case, the tangent squared plus 1. No a to factor, it's just a 1. But that's just our Pythagorean identity, secant squared. The Pythagorean identities are indispensable with this work. So if you're rusty on them, you're not anymore. So now when we do the square root, we have the absolute value of the secant. So now let's go ahead and test our limits, and this will be easy. We just have the x equal tangent theta. So first, let's do 3 equal tangent theta. Unfortunately, this is not an easy one. I mean, this is just what it is. In this case, theta is just the inverse tangent of 3 radians, and that just is what it is. And we'll make our triangle so that when we actually try to evaluate the integral, we can use the triangle. I used to do problems like this with the face-to-face, and then they kind of fell out of favor, and then now they're back. So it just really depends on what the class needs. So now 1 is equal to tangent theta. And of course, this is a unit circle value, pi over 4. So we have inverse tangent of 1, which is pi over 4. So now we see that we have the pi over 4 as a lower limit and 3 as our upper limit. So this is where we know that the inverse tangent has the positive value. So we will select the positive here. So now, again, just a little diversion from the regular path since we have limits. And if you like, we can go ahead and draw a triangle. The issue is right here. So when tangent theta is 3 over 1, we can think, oh, well, let's just look at this. Notice here, let's just say, I guess what we can do is think of it this way. Yeah, we can just think of it this way. 3 over 1, and then a square root of 10, like that. So the idea here is normally we would have variables. So since this one is the difficult one, we know this one easily, but this is the difficult one. So we'll just do tangent theta is 3 opposite over adjacent, and then use the Pythagorean theorem. And that'll help us to evaluate values that may come up in our definite interval. So I was thinking I'll change the variable, but this will work fine. So now let's fill everything in. So the only issue here is that we have the limits, and then of course we have to negotiate the trigonometric interval. That's why I thought this would be a good example. And then the upper limit is just the inverse tangent of 3. Now, of course, the square root of x squared plus 1 will be secant theta. And then, of course, x is tangent theta. So when you think about it, ladies and gentlemen, trig sub is miscellaneous substitution. We completely transform the integral. And then we have secant squared theta d theta for the dx. So what you're seeing here is that this is pretty much standard fare, but we have this little additional computation here because of the definite integral, but not a difficult thing. That's just pre-cal. Now we can see, what does this give us? Pi over 4 inverse tangent of 3, and that'll give us a secant cubed. Well, you know, why even bother to do that? This makes sense. It's already set up for us. Let's just go ahead and write the secant squared as the Pythagorean identity. And then move the secant over. No need to go forwards to go backwards. So we'll do tangent squared theta plus 1 over tangent theta. So much of what we do in calculus is looking into the next step, and we sometimes fall over ourselves trying to get to the punchline. So again, if you already see the use of the Pythagorean identity, go ahead and use it. No need to multiply and then break it up again. So this will give us pi over 4 inverse tangent of 3, and now we can divide. So this will give us tangent theta, and then 1 over tangent is just cotangent, and now we multiply by secant. So this will give us, well, at least things we can anti-differentiate. That's the whole key here. Maybe we do about the same amount of work with these trig integrals. Some just require the reduction formulas, or just straightforward application of reduction identities, power reducing. But this is just basic identity manipulation. So we have secant tangent. Now notice, and this is something I can see right here, cotangent theta is just cosecant theta over secant theta. You just rewrite the cosine over sine as cosecant over secant, and then you see the secants absorbed. So that's a little trick you learned in pre-cal. So that's cosecant. And we know how to do those integrals. The idea is that you can always convert to sines and cosines, but I've been trying to teach the use of the Pythagorean identities because they get to the punchline a little quicker and more efficiently. But again, that's your choice. It doesn't matter. You all get the same answer as long as the reduction is adequate. So now the antiderivative of secant tangent is just secant. Excuse me. Now, if you will, and I guess it doesn't really matter at this point, we'll go ahead and put our limits on the whole thing. And then, of course, this is one of our Lagrange integrals. Remember, we get the negative of the natural log of cosecant plus cotangent. And of course, you can move the negative inside and switch the plus to a minus, but let's just go ahead and write it this way. So these are, we do the secant integral all the time, and that's one we're used to, but this one we also know from Cal 1. And then we evaluate, excuse me, from pi over 4 to inverse tangent of 3. Sorry, it's getting a little bit crowded there. Let me just do a little, so you'll see that separate. So now let's go ahead and evaluate using the fundamental theorem. So we'll have secant, this is where our triangle is going to be useful, secant of inverse tangent So that's how we're going to use the theta in the triangle. So you see it's already set up. Minus natural log cosecant of inverse tangent of 3 plus cotangent. Well, the fun never stops, right? Oh, well, we know what this is. Let's just be lazy here. Cotangent's 1 over tangent, right? So those just write that as 1 over tangent of inverse tangent. That's just going to be 3 downstairs, but I'll just be lazy and do that. And then we've got minus secant of pi over 4, fundamental theorem. And then we'll have minus minus, so we'll have plus natural log cosecant pi over 4 plus cotangent pi over 4. Right to the edge of the page. Nothing like the overhead or the overhead, my document can. So now, but see, let's just look at this. Everything we've done here is basic. There has been nothing elaborate except this, just the trig substitution. Everything else is the standard fare. Trig integrals, which are going to be tested on this test, calculus 1 integrals, fundamental theorem. Nothing unusually difficult, just lots of steps, but you see where you're tested on all the different pieces. So that's what makes this problem a little bit multi-step in the sense that we have more steps. So now we can use the triangle. So we have theta here. So we have hypotenuse over adjacent. So that's square root of 10. And now we have cosecant. So that will be hypotenuse over opposite. That's just the flip of the sign. And then, of course, this is 1 over 3 because these are inverses. I always have trouble trying to convince my pre-cal kids that this is really stuff they need to know. And then, of course, secant of pi over 4 is just root 2. That's why I always write cosine of pi over 4 is 1 over root 2. So my students remember that reciprocation is easier when you don't rationalize. And then plus natural log. So we have cosecant, same thing, pi over 4, root 2. And then cotangent of pi over 4 is just 1. So now we can combine all of these if you like. This is just a square root of 2 times square root of 5, and we can factor that. So we could say square root of 2 times the square root of 5 minus a 1 if you like. You certainly don't have to do that, but I like to factor things. That's fun. And then now we can consolidate these using the quotient rule for logarithms. The square root of 10 plus 1 is downstairs, but then the 3 will flip and run upstairs. So this will be plus the natural log. And of course, we can remove the absolute values. 3 times the square root of 2 plus 1 divided by the square root of 10 plus 1. I reduce that to this. And of course, you can write this as 3 times the square root of 2 plus 3 if you want. Again, this is exact. Now, lots of times in the WebAssign, there will be instruction to give an approximation. But that doesn't occur all the time. It rarely occurs. But when it does occur, you take your exact answer and you can use, in my pre-calc class, I use my Google calculator, which is the free calculator online, and it's magnificent. It gives beautiful output, easy to use. I mean, it's old school, but it works really nicely. And when I actually computed this, I got, well, I ran this out to 4 decimals. So I got approximately 2.3019, or I guess you could round that to 3 decimals, 2.302. And I thought about that when I thought about your WebAssign. This would be a nice problem where they would probably say approximate to maybe 2 or 3 decimals or whatever. But I don't care about that. You can do. You could do that as a general math student. This is what I care about here. And then if you get this right, then that's trivial. So again, the important thing here is we go back to a topic that we learned at the beginning of the class where we were limited as to the techniques of integration. And so every part of this problem is Cal 1 and pre-cal. Basically, this is pre-cal, but we just don't talk about it, or Cal 1, we just don't talk about it until Calculus 2. And so with the trigonometric substitution and the use of the trigonometric identities, the Pythagorean identities, we can transform this problem into a doable problem. So we get a really, really elegant solution here. The thing is that this comes a long way from where we started in Cal 1, now that we can actually get an exact answer here. So this is a good example to kind of showcase all of the different types of trigonometric techniques that you use in Calculus 2, or all calculus, and you will use these over and over and over. Again, those of you that end up in the electrical engineering, do the Fourier analysis, the infinite expansions of sines and cosines, that will, again, put this in your realm every day of your life. And even as a professional, you will continue to work with the trigonometric series. So really a good problem. And thanks to Dr. Larson for crafting these really nice problems. All I have to do is look in your book and I find these problems and boom, we go at it. So again, the WebAssign and Dr. Larson's book provide us with good examples to become better future STEM professionals. So now what I want to do is talk about the partial fraction decomposition. Now, you think about fractions and you think about rational functions and you think, well, that's not so bad. I can do that. That you know, but we're always accustomed to getting a common denominator. Now what we want to take a fraction and we want to decompose it. So for instance, we might have an integrand that's a rational function and we want to break it up into pieces and hopefully be able to integrate the pieces. So what I wanted to first share with you is a simple example. Then I'm just going to give you a couple of rules, but the rules are best learned through doing examples. So I want to first start out by doing a very useful, it's a twofer, so to speak. We do one integral formula, and then we get another one for free. And this comes up so often in engineering and physics. And this will be like the special integral formulas from last week. You know, the square root of a squared minus u squared, the square root of u squared plus a squared, and the square root of u squared minus a squared. Remember those special integral formulas? Use them to good health, okay? We go over a formula, you are welcome to use it. You should use it. So for partial fractions, there'll be times just like in trig sub where maybe we don't have a formula that we have right on the tip of our tongue. And so we use the trig sub technique. With partial fractions, we do the same. Maybe there's a formula that comes up all the time and we just remember it and we're not going to reinvent the wheel every time. So here's a formula like this. For instance, take a to be a positive number like we do in trig sub. And then, of course, we're going to suppose that u is a differentiable function. We always write these formulas in u's. Suppose u is a differentiable function, at least on some set of content. You can get into strange functions when you take topology, some of you that take more mathematics, and we'll leave those to topology right now. Right now, we need a set of integration and differentiation. So what I want to do is consider the following. Say we had the integral with respect to u of a squared minus u squared. Now, you might be looking at this and say, well, we could use a rigged trig sub. You know, we could do sine, you know, a squared minus, you know, u squared, and then square it out and to the first power, things like that. And that always can open the door for us because we know the inverse sine form. And we're thinking, well, could we rig that in a way to get the same output? And absolutely, you can do that. But what I want to show you is a method that's going to take us beyond that. I mean, sure, this is Pythagorean, and we have other ways to do it. So that's fine. But I want to show you a different way to do this problem that's going to open the door to doing other examples that aren't necessarily Pythagorean. So here's what we're going to do. We're going to decompose this integral. So what I want to say is we use partial fraction decomposition. I mean, when you're doing integrals, ladies and gentlemen, you can use whatever technique you want, but you are in charge. I mean, the interesting thing about life is that if you get the job done, that's what's important. And in mathematics, that's what we're looking to do. So 1 over a squared minus u squared. Well, what I'm going to do first is factor. You're going to say, oh, well, Professor Ron, this is a difference of 2 squares. So now what we're going to do is look at this as 2 linear factors. Notice we have degree 1 in u and degree 1 in u here. We call these 2 distinct linear factors. So we have distinct, it's like we're doing the quadratic equation, distinct linear factors. So when we have distinct linear factors, there's a set method to decompose, and it's always the same. We simply take a coefficient. I use uppercase letters. Dr. Larson tends to use the uppercase letters, but again, that's up to you. I like the uppercase letters so that we don't get confused with other lowercase ones. So we'll have a minus u. And then we'll have plus b over a plus u. So when you have distinct linear factors, maybe you have 2, maybe you have 3. If you had a third distinct one, then we'd have plus a c over that distinct linear factor. This is how we decompose fractions under this hypothesis. And then, of course, if we have a repeated linear factor, then we just have the repeated linear factors of that power, say, square and a b. So you do things that you would normally do, but you don't think about this because you don't usually think about undoing a fraction. You're always interested in putting 2 fractions together. So this is going in the opposite direction. Now, the key here is the algebra. At this point, what we want to do is clear denominators. So I want to multiply through by a minus u times a plus u and clear the denominators. So When we do that, over here, these will absorb, we get 1. And then when we multiply by a minus u times a plus u, we're left with a times a plus u. And then, of course, the a plus u absorbs here, and we're left with b times a minus u. So we clear denominators, basically like we're doing the least common multiple thing in college algebra. This can also be understood with the Heaviside cover-up method, but this is so simple to do this, we're going to adopt this because it's easy. So we cleared the denominators, and now we have an equation that's true for all u, or x if we were using x. And so what we want to do is now, as opposed to multiplying everything out, even though sometimes that would be good, we can just substitute convenient values of u to figure out what the coefficients a and b should be. So first, we're going to start out with u equal negative a. So if u is equal to negative a, the 1 is independent of that. That absorbs, and here we have a b times a negative what? In this case, we have a minus a negative. Let me write this out. Minus a negative a, and that gives us 2b. So b is 1/2. You know, and what's interesting about all of this is that it doesn't matter how you set this up. It doesn't matter which a goes here or b goes there or whatever, just so long as they're distinct. And so what I'm saying here, if we use the minus a for u, this term goes away, and we only have an equation with b. So a minus the negative a gives us 2b equals 1, so b is 1/2. Now, of course, let's play devil's advocate and do the same thing. Let now, in this case, let u equal a. So the 1 is unaffected. And now, of course, here, if you look at this particular situation, we're going to have, in this case, a is equal to 2a, or a plus a. Oh, let's see. In this particular case, let's see here. Oh, I'll get it right. You all think I'm probably losing my mind. I need to keep these letters hanging around. So we've got b times 2a. So b is 1/2a, forgive me. And now let's keep going. So here we have a 2a, and we get the same thing. A equals 1/2a. I'm doing this in general, so I can't forget the little a's. Okay? So again, let me just recap. What we want to do is use values of u that are easy. So if I use negative a, I get 2 times lowercase a times b. I can solve for b, and b is 1/2a. Now, if I want to eradicate this term and just solve for uppercase a, I can do that by letting u equal lowercase a, and I get a times 2 times a, little a. That's why you see we're using the lowercase and uppercase, and we get this. So now we've got 2 simple coefficients. So this implies that the integral du over a squared minus u squared, let's just go ahead and fill it in. We have 1/2a, a minus u du, plus 1/2a. The mathematics always tells us what to do, that's for sure. Now, of course, this is just a du over u, but notice we have the negative, so we need the negative out front. We need a negative here and then negative to pay for it. So this will be negative 1/2a ln a minus u. Now, of course, we have no negative here, So this will be plus 1 over 2a ln a plus u. When it's so easy, it's sometimes difficult, plus that arbitrary constant which we need. Now, just to make this look pretty, so to speak, we're going to use the laws of logarithms and factor the 1 over 2a. So this will equal 1 over 2a, and then just do the ln of a plus u divided by a minus u in absolute value. Now, this is what I'm talking about, ladies and gentlemen. Even though we have more letters hanging around, this is a very famous formula. So now I'm just going to write it. I'm just going to write it here to the side, put all the stuff together so you can have it nice and appended. du. And if you can put it on a note card and remember it, you can use it. So again, this would also work with the trig sub, but we want a more generalized method. So if you encounter this, and then of course you're thinking, you can flip these around. I mean, it wouldn't matter with the absolute value. You can write this as u plus a, and then of course u minus a. That doesn't matter. Those can mix and match because of the absolute value. But now, of course, what if we had the integral of u squared minus a squared? That would just be the additive inverse of this. So this implies that the integral, and sometimes these aren't even written separately in the integral table because they assume you would know this, but let's just go ahead and write it down anyway. This integral is just the additive inverse of this, so we have the minus, and so we can run it upstairs with the power rule and flip the fraction. So this gives us another one for free. So talk about efficiency. And then of course, if you like, you can flip these around. U minus a, it doesn't matter, absolute value. Whatever sign doesn't care, and you shouldn't either because they're equivalent. So what we're seeing here is that by using the partial fraction decomposition for linear factors, even though we have another method available to us, we can get two very nice formulas that we don't have to always redo when we see them. The idea is that this is a common occurring integral, especially in physics, electrodynamics. And so it's like, okay, there's my favorite integral. I'm just going to go ahead and write down the antiderivative. And then, of course, what's nice about this, if you have the additive inverse, you can just flip this using the power rule. But what's good about these integrals is that you remember one. Don't try to, like, you remember the derivative of cosine is negative sine, then you're fine. You don't try to memorize everything. You set up patterns that way. So remember this, and then when you encounter this, just remember to flip the fraction. Or you could just leave the minus out front. But you know what? We forget minuses. So if there's a minus out front, we forget it. If we move it up with the power rule, it's built into the formula. So basically, the fractions just flip. That's all. So what are we doing here? In general, so that gives us a, well, okay, here we go. So if we were going to do an example, let me just give you a simple example with this. Say you had this. And we'll just use our integral formula. Say we had something like this. So this is x squared minus 4, so u is equal to x. So we have u equals x, du equals dx, and a is obviously 2. So now, if we just use the formula here, we just go back to our formula right here, this one. So we have 1 over 2a, so we have 1 over 2 times 2, natural log, 2 minus x, 2 plus x, plus a c, and then of course 2 times 2 is 4. So the idea that we see with these kinds of problems is that if we encounter particular integrals that are often in our plate, we don't want to have to stop and do the same thing. These are very mundane calculations. This is basically why I went through this. But when we don't have this beautiful symmetry here, we don't always get these really nice coefficients. But at least we know how this happened. Now, in the general case, and let me give you the general case here. When you think about, and this is from the lecture notes that I have posted online, when you think about a rational expression, ladies and gentlemen, and I did the same thing up here as another type of exercise. You first think about the fact that you want the numerator, I mean, if the numerator has a larger degree or equal degree, you want to divide. So then you get a quotient, which will just be a polynomial. And here you'll get a rational expression, okay? That's where we want to apply these rules. First, we want to make sure that we have the degrees set up in a very convenient way. And then here's what we want to do. This is what we want to think of. We're going to be able to look at D as factored over R. It's either going to have irreducible quadratic factors like x squared plus 1, or it's going to have these linear factors. And so what we're going to do is what we just did in the last example. If we have a repeated factor, we'll start with the first power and go up to that repeated factor. Well, we didn't have that in the last case because we just had one factor of each distinct linear factor. So we just had this term, and then we had another term with a different denominator. And the same with the quadratic. The quadratic, again, require a linear numerator. Here we have a constant. With the quadratic that's irreducible, we must have the bx or b1x plus c1. We have to have a linear factor upstairs in order to affect the decomposition. And we just ascend to the largest power that this repeats. So that's just that's the basic rule, which basically appeals to our intuition. So when we look back at the original problem here, we only had to the first degree each of these distinct factors. So we just have an A and a B. Now we could do A1, A2, A3, but that gets confusing. I just use the letters of the alphabet, and rarely would we ever run out. And this is much easier to keep track of. And then of course we did this in the abstract, so we didn't have a bunch of numbers. For A, instead of, we would have like maybe a 3 and maybe a 5 or something. And if it were the same type thing, maybe like we have in the problem that we just did, we had a 2 and a 2. So the idea is that we have to work a little bit harder when we want a generalized formula, but then of course it pays off handsomely when we have a nice integral table formula. So let's go ahead and apply these rules. Again, these are in your lecture notes, and I just wanted you to be a bit aware of them, basically how we're going to work with these types of functions. Now, let's look at another example where we actually have to divide. So let's get a new clean sheet here. So here's a WebAssign example. So I want to showcase what I just talked about. So say we have something like this. So like we're in a pre-cal class, but the professor doesn't give you the integral sign. So we have x cubed minus x plus 3, and then we have x squared plus x minus 2. So you're thinking, once you learn a technique, you can develop your own integration formulas with your own letters. I mean, you have the ability to do that. So now what we're going to see here is we've got a situation where the numerator has degree 1 larger than the denominator. If they're equal or this one's larger, we want to divide first to get a quotient plus some stuff, which we can apply our decomposition techniques to. So let's go ahead and divide. This is very easy. Can't use synthetic because, well, obviously it's not Bionic of degree 1. So this is mundane but easy. X cubed, and of course we have a 0x squared, just put in a placeholder, minus x plus 3. That way our columns are aligned and we don't forget things. Let me check the, there we go, always go for the good focus. So now we get an x, so we get an x cubed, and then multiply, so this is a plus x squared. This is just division of integers if you want to think about it, and then a minus 2x. The division algorithm for numbers is the same for polynomials, even though the proof for the polynomials is harder. So when we subtract, these absorb, and we get a minus x squared. And then here we have a minus minus, so we get plus x plus a 3. So now this degree is the same as this. Division algorithm says we can continue to divide. So we get minus 1. So we get negative x squared, and then a minus x, and minus minus plus. And then the division algorithm says we subtract to figure out our remainder. These absorb clearly, and then we get what, a 2x plus a 1. Now, the division algorithm at this point says, okay, you need to stop dividing because this degree is 1 and this degree is 2. So this is clearly the remainder. So now, and what's so funny about this, WebAssign always says, okay, if this is an easy integral, do the easy integral. Do not hurt yourself applying a technique. I mean, it's good to learn how to use a technique, but don't use it unless you have to. So now, we have x minus 1. And then, of course, we have 2x plus 1 divided by the divisor. Now you're thinking, Santa Claus came early, because it's like, well, Professor Ron, we want to practice the decomposition. Well, we practiced it, you know, to develop 2 theorems or 2 formulas. But when it's easy, it's easy. So look here, that we can do in our sleep. But notice here, if this is u, we have u, it doesn't come any easier, ladies and gentlemen, x squared plus x minus 2. du is what? 2x plus 1 dx. Shazam. It's like, well, I'm done with this. Now, here's the thing. You're looking at this and say this factors, and that's true, but this is where the WebAssign always says, if you need it, if you need the technique, use it. If not, don't worry about it. So now we're good to go. That's a du over u, and that's table ready. Can you believe it? Do we ever get integrals that easy? So the WebAssign, like I said, is smarter than we are. I think these algorithmic generated problems they code things in a way to have this happen, which is really neat. So now we get what? X squared. Well, what do we do? X minus 1 squared over 2. That's an easy integral, because if you differentiate that, you get x minus 1. And then here, this will be what? Plus ln of the absolute value of x squared plus x minus 2, plus a constant. That was easy. So the thing here is, if it had turned out that this wasn't nice, then we would have to rig it like we've done before. We'll do one of those today. Fix up the coefficients, and then with the stuff that was hanging over, we would have to use the decomposition technique. But when it's easy, it's easy. And so that's an easy antiderivative right there. And then of course, this is an easy antiderivative where we see that on occasion, some of our examples are indeed this easy. Now, of course, if you wanted to break this up and factor it, you could just do this as a sum, but that's fine. So we are done. Just note, easy integral, easy, this one right here, easy integral. So always look for ways to cut down on the work. We found with the warm-up problem that there really weren't any shortcuts with that one. We were stuck with it. Now, let's look at one. Before we get on to the quadratic factors, I just want to practice one where we do the linearized technique with a definite interval. So let's look at this one. 0 to 3. So we want to do a definite interval, lower limit 0, upper limit 3. And now we've got 4. And we got 5x squared plus 6x plus 1. Now, if we look at this problem, ladies and gentlemen, it's very different from the last one. With the last one, we first had to divide because the degree upstairs was 1 more than the degree downstairs, just like doing horizontal asymptotes in pre-cal. And so we get a very simple setup here, which we were easily done with. Now, in this case, we have the degree upstairs is 0 and the degree downstairs is 2, and this will factor. Plus, again, you think about this, sometimes if it doesn't factor and you're getting, irrational 0 type situation, then you've got maybe the inverse tangent set up. You get a number of things that can get into the mix here. So again, never underestimate a quadratic. We apply whatever technique will get us where we want to go. So now we're thinking we don't have to divide. So let's go ahead and say, okay, well, I don't think we have to complete the square because 5 times 1, 5 plus 1 is 6. So that's Professor Ron's AC limit. So we have 5x, we have an x, and then we have a plus 1 and a plus 1. Now, one thing that I like to factor things to death, but when we're working on problems like this, it's probably best to go ahead and keep all of the numbers in the factors, just with the thought that we can adjust this fine, but we want to keep all the factors in place. You might want to factor that, 5 and get x plus 1/5, and that's fine. You want to think that way when we actually try to decompose. But just as maybe a word of caution, let's keep everything within the factors here, and I think we'll be okay. Now notice here, we need the partial fraction decomposition. We don't have a nice formula that we can use. We don't have the a squared minus u squared or the additive inverse of that. So we're just going to decompose this. So first what we do, we'll come back to this, just leave some space, we'll fill it in. Now we need to decompose. So we have 5x plus 1 times x plus 1. And we always want to use coefficients or either differentiate or use values of x that make our determination of the coefficients easy. So first, we'll do a divided by 5x plus 1. So these are distinct linear factors. And then we have b over x plus 1. Now, say you're working with someone and they flip everything around. Doesn't matter. The result will be the same. The idea is all of this is consistent with real numbers. So do not worry that you have a different approach Good mathematics produces the same result. So now we think we want to clear denominators. So we're going to multiply through by 5x plus 1 times x plus 1. Of course, now on this side, that will retire both of these and leave us with a 4. And then we get a times x plus 1 plus b times a 5x plus 1. So this is a visual. This is symbolic computation. So when we multiply by the factors here, this absorbs, leaves us with an x plus 1. The x plus 1 absorbs and leaves us with the 5x plus 1. So now we're going to pick convenient values of x to solve for a and b because we can. So now we'll just say u equals -1. Now you're thinking I should have started this way instead of doing the abstract, but we survived. Just have to remember you've got the little two times the little a and not forget that. So now this absorbs, so we get 4. And then we put in the -5 or -1, so that'll be a -5. So we have b -5 plus 1, which is -4b. So the 4 is absorbed, b is -1. So very easy computations. Only, do enough steps so you can check and go back and check. We substituted -1, here absorbs, -1 here, -5 plus 1, -4, the 4 is absorbed, b is -1. So we're done with that. Now over here, again, just kind of think about this. This is just what, 5 times x plus 1/5. So we can do -1/5 to absorb that. So u equals -1/5. So we have 4 equals, so we have a -1/5 plus 1. So of course that'll be 5 over 5. So -1 over 5 is 4 over 5. And so now the 4 is absorbed, and we just get, in this case, a over 5 equals 1, if and only if a equals 5. All right, that's something on the desk. Okay, so notice now we have our two coefficients just by using convenient values of x. This is the way to do it. Use convenient values. I'm going to show you some other tricks. Otherwise, you got to multiply all this out and compare coefficients, which you're going to learn how to do in differential equations. Unfortunately, the method of undetermined coefficients is a waste your time. But sometimes you have to do it. I try to teach different methods. I don't know, but methods that are long-winded are just sometimes unfortunate, but necessary. So here, we're good to go. So now let's go ahead and fill in our integral. So now we've got the integral from 0 to 3, 4, 5x squared plus 6x plus 1 dx. And now this is going to equal, so we're going to fill this in, a is 5, so we have the integral. Now this is what you can do just to save a little bit of time. You can do these separately or run them together. So we've got 0 to 3, so we have 5 over 5x plus 1. These are easy integrals. And then we have -1 over x plus 1. So now, again, sometimes we're like, the math gods are too good to us. This is table ready. We got 5x plus 1. The du is 5 dx, and boom, there's the 5. So that's table ready. So we get natural log of 5x plus 1. And then, of course, this is table ready with a minus. So then we get minus natural log x plus 1. So when it's easy, ladies and gentlemen, it's easy, 0 to 3. But you see the power of the partial fraction decomposition to take the distinct linear factors figure out the coefficients, break up the power, the rational denominator, so to speak, to now you're thinking, well, this is going to give us a bunch of du's over u's. If they're linear and distinct, we'll get du's over u's all the time. So what happens here in this particular type of situation is that you get very simple integrals that don't take much time to do. So that's another plus. So now we'll do the fundamental theorem. So we have natural log, and we'll have a 15 plus a 1 minus natural log. So we have, in this case, make sure that's a 3. We have a 3 plus a 1, so that's a 4. Now we have minus, put in the 0. We have log of 1, and then minus minus plus log of 1. So now when we look at this, we don't have much left in the way of computation. Now, one thing that we notice when we do these types of computations is that we've got 2 zeros here, and then we can just use the difference here, the difference of 2 logs to write as the quotient of a log, if you like. It doesn't matter if you don't. So this will give us ln of 16 over 4, right here, these both being 0, which would just be natural log of 4, or if you like, power rule 2 log 2. So this particular problem, again, you don't have to do this. We'll just say quotient rule. And then, of course, these terms are just 0 by definition of the logarithm. So the idea is that now, with the partial fraction decomposition, we see that on occasion, we can, if we notice that the denominators are Pythagorean, then we can use trig sub. But as we saw in the very first formulas that we derived, even though, you know, we chose to do partial fraction decomposition just so Professor Ron could introduce the concept, here we have distinct factors. So we don't have the option of creating a denominator that would be more user friendly. You can always rig things to use whatever method you like, but we can just see here that by using the partial fraction decomposition, we do get something that is user-friendly and easy to effect. So just remember, you always have choices when it comes to doing integrals. You learn a new integration technique and you want to use it. And so sometimes you may use it when you don't even need to use it, but that's okay. It's good to practice. Now, the next technique, we want to look at a irreducible quadratic factor and see how we can work with that. So again, when I talk about the fact that no particular technique that we use is unique, I mean that you are in control. So you use the technique that you find to be the simplest. So let's look at this one. Here's a WebAssign problem. 7 minus x squared divided by 5 x cubed plus x dx. Now, when you look at this problem, again, it's similar to the last one in that you have the degree upstairs is 2 and the degree downstairs is 3. So this is set up. And of course, you can factor the denominator into an irreducible quadratic and into a, as we want to say, linear factor. So let's do that. So factoring the x, we have x times 5x squared plus a 1. Now, of course, like I said before, you can kill things factor wise. You could go ahead and factor the 5 and be good to go, and there's not a problem with that. But what I want to emphasize here is that when you're actually working these for the first time, just go ahead and keep everything within the factors. That way your computations will still be doable, but will allow you not to have to remember too many residual coefficients. But again, however you choose to do this is fine. I think most students just look at this and say, well, I'll deal with the 5 there. I'll be okay. Now notice we have a distinct linear factor and we have a distinct irreducible quadratic. So we say 5x squared plus 1, irreducible quadratic, over R, of course. And then we have x linear. So now what we want to do is decompose this integrand and then figure out our coefficients and be done with this problem. So now we have 7 minus x squared divided by x times 5x squared plus 1. Whatever algebra you do to the problem is always fine as long as it's consistent. You don't have to worry about it changing the problem or making it incorrect. If it's legal and puts you in a better level of comfort with the problem, then do it. So now we'll just say a over x for our linear factor. We just need the numerator a, the constant, plus, and now of course we need the linear coefficient here, the bx plus c. So when we decompose a fraction that has a linear factor in irreducible quadratic, we must have this decomposition. Now this doesn't say anything about a, b, and c so much. We will know that we will have to determine the a, b, and c. And based on our computations, one of them, the c might be 0. We don't know. We work forward. We know that if we decompose, this must be the decomposition based upon our rules. So now, let's go ahead and clear. So multiply by x times 5x squared plus 1. That'll clear everything out on the left-hand side. When we multiply here, the x goes away, but the 5x squared plus 1 stays around. And now with the bx plus c, the 5x squared plus 1 goes away, but the x sticks around. Okay, now what I want to comment on here is that the clearing of the denominators is essential, because now this will work for any real number and you don't have to worry about dividing by 0. We transform. It's like we transform to an equation that is true for all values of x. And that's what allows us to choose these convenient numbers. This is a technique that is, again, based on Oliver Heaviside's techniques that we've already referred to. The man was a genius, and his techniques are still used widely long after his death. It's like he's like the Newton of engineering mathematics. So now, if you look at this, and you might look and just say, let's just go ahead and clean this up a little bit. So we have 7 minus x squared equals, I'm going to say 5a x squared plus a, let's go ahead and multiply it out, plus bx squared plus cx. Okay, just very simple. Look what I did, 7 minus x squared, 5ax squared plus a, bx squared plus cx. Now, notice here, here's a real easy thing to do. Let's just let x be 0 to kill everything except the a. So if x equals 0, we have 7 minus 0, 0, a, 0, 0. A is 7, right there. So We do the easy stuff first. And then I want to show you a technique that I actually learned as an undergraduate, but is rarely taught. This is a differentiable function. So let's differentiate, and then we can use zero again if it helps us get where we want to go. So at this point, you're thinking, gotta choose another number. Well, the number, we already used zero, and we can't use that again. So let's differentiate and use zero for the different equation. So differentiate. This is a Professor Ron technique. So let's differentiate. So now we get the zero, so we get the minus 2x. Okay, here we'll get the 10ax, by the power rule, 2 times 5, 10ax, 0 plus 2bx plus c. Okay? Now this is what I was telling you. When you differentiate, then you can use zero again. Zero is our friend, ladies and gentlemen. So now let's differentiate. Let's try x equals 0 again. I'm always going to give you the clearest, most efficient path, even though sometimes that path is long-winded. So now if we let x be 0, 0, 0, 0, c equals 0. C equals 0. Done with that. Okay? And then, of course, I could have just put in the a is 7 here, but I didn't need it. I didn't need it because I didn't care about it. I just zeroed out that term. So now let's differentiate again because we're lazy. Differentiate. So we get negative 2 equals 10a plus 2b. And now what we want to do is we want to figure out what b is. Now, here's the thing, and this is where you're thinking, oh, okay, I see, Professor Ron. So we know what a is, and we can find b. First, we got extra stuff, so divide by 2. So I got a negative 1 plus 5. Oh, sorry. Always follow the symbols. Divide by 2, negative 1 equals 5a plus b. And now solve for b. b equals negative 1 minus 5a. But a is 7, so we get negative 1 minus 35 equals negative 36. That's b. This is the quickest way to get the coefficients. I defy you to find another way to do it quicker. This is easy, and you won't mess it up. You multiply everything out, compare coefficients, and you'll make five errors. I've decided that this is an easier technique when you have irreducible quadratic factors because I got tired of seeing students mess this up. So differentiate, set 0 for x. Now then, of course, you can differentiate again, and since you know what a is, you can find b with minimal effort. Okay? So now let's go up to this equation and finish the problem. You know, if you find yourself writing down a system of equations to solve for the coefficients, then that's called overdoing it and is wasting your time. Don't waste your time. I won't waste it. So now let's go up here. We've got a, boom, right there. So equals 7 over x. Let's just write down everything we have, plus, and then we have b, which is negative 36x. And c is 0, so, well, lo and behold, 5x squared plus 1. So you look at this and say, well, the math gods are smiling at us again because these are easy integrals. Notice this is a du over u. This one's table ready. Let's make this one table ready. So we have u equals 5x squared plus 1. So du is equal to 10x dx. Now, of course, we could be all fancy with the coefficients, but we'll just put in the 10 and divide by 10 and not worry about hurting ourselves. So this will give us the integral. Just write these out, dx over x. And then we've got what, minus 36 over 10, 10x dx, make it table ready, 5x squared plus 1. So again, we make this table ready and pay for it, and then don't worry about that. So that'll be 7 times the natural log of x. And now, of course, here, that's going to be what? 18 over 5 if we divide by 2. Natural log 5x squared plus 1. Of course, you don't need the absolute values there, but if you use them in your WebAssign, then that's fine. No big deal. So what we're seeing here is the actual integrals that ensue are easy. That is, when you work these kinds of problems, you may have to do some finagling with the coefficients because you get like a Cal1 integral mixed up with an inverse tangent integral or something like that, where you've got to break things up and be clever with the coefficients. You all know how to do that. Now, the thing again that I want to emphasize here is we are better off at least keeping everything, you know, in-house for now with the coefficients. I know factoring is something you want to do, but notice by leaving the 5 here, we have a nice clean equation. So once we get the coefficients, we can move from here to here. All we do is add the integral sign, just like doing the trig sub. We're doing a reduction formula for a trig integral, like we did sine of what, to the 6th power of 3x or something that we did. So the idea here is that if you have an equation where you clear the denominators that will be valid for all values x, you use the simplest value of x you can. In some cases, it may not help you, but always try 0. And then, of course, if you differentiate, try 0 again. You will have a different equation, but these are all equivalent. When we differentiate, the relationships with the coefficients, they do not change. These are valid operations. And the power of the differentiation is that it's easy. It's easy. Multiply things out and then differentiate and check simple values of x. And then, of course, as you learn these, you may have to eventually substitute for them, and then you're good to go. The technique here, I don't want to make it look like it's just trivial, but it is a technique that will move the calculation forward with simple computations. That's really what we're looking at here. We want to keep the computation simple and not worry about elaborate, very difficult arithmetic operations. Keep everything very straightforward. Good example. Now, let's look at another. I mean, if you can do the irreducible quadratic functions, ladies and gentlemen, you can do anything. So let's look at one of these. Here's another WebAssign. And let's see what I've got here. Oh yeah, I've got another. The problems never end. We can do math problems all the time. So let's look at this one. Remember, always divide first if the degrees warrant that, and then check to see what you have. If the computation can be done using simple Cal1 techniques, then do it. Don't bring out the major artillery unless you need it. Again, that's just for efficiency purposes. So let's look at this one. Here's x squared plus x plus 15. You can make up these problems. The beauty of it is that you can make them up once you run out. And then we have x to the 4th plus 30x squared And this is a repeated one. This is why I want to do this one. So this is one of those integrals that you don't wish to encounter. That is, you have x squared plus x plus 15 divided by x to the fourth plus 30x squared plus 225. Now what you see here is a perfect square, because that's 15 squared, and this is just 2 times 15, which is 30. So this is a perfect square. So that's kind of obvious, but even if you didn't get that, you could use Professor Ron's AC lemma and get the same result. So like I tell my pre-cal kids, they don't seem to think that writing a problem down correctly is important. And if an uppercase A is used in the problem, they can't use a lowercase. Again, that's a big mistake, but we do it because we don't pay attention, because we're human. And they have to learn. They have to get up to your level. They're trying to learn how to write problems correctly. That's still difficult. So now we have x squared plus 15, quantity squared. So again, x squared squared, x to the fourth, 15 squared, 225, and then 15x squared times 2, 30x squared. So that's the perfect square. So what we have is a repeated irreducible quadratic. So repeated irreducible quadratic. Now, when we worry about these types of problems, or we do these types of problems, we notice that the rules give us the algorithm to solve this. So again, we have no linear factors, which is unfortunate, because we like the linear factors. They're easy. But I will say this, and this is important. When you actually work through problems and you notice some simplifications once you get the coefficients, that's the payback. So now let's do the decomposition. So x squared plus x plus 15. And then we have x squared plus 15 times itself. So remember, we have a repeated irreducible quadratic. So we have one term with the first power of the quadratic, and then we have the second term with the second power. So we ascend to the highest power, which is 2. So we have ax plus b divided by x squared plus 15. Remember the rules that I showed you. You see these in your lecture notes on Blackboard. Plus, then we change, we could do A1, A2, A3, A4, but we use the different letters because they're easy to see. Cx plus d, and then we have x squared plus 15 quantity squared. So now what we want to do is clear denominators. So once we set up the decomposition, again, once you set up the decomposition, clear denominators. So multiply through by x squared plus 15 to the second power. That will absorb the factor here. So we get x squared plus x plus 15. And here, one of the factors will absorb, but we're left with one. So we have ax plus b times x squared plus 15. Okay, so again, not as simple as we would like, but something we can deal with. And then of course here, all the factors absorb, and we're just left with the cx plus b. Now, what I would do here is go ahead and clean it up like we did before, and then we can use 0, and then we can differentiate. So first, equivalently, x squared plus x plus 15 equals, so go ahead and multiply this out. We're going to get ax cubed plus 15ax, just hit everything with an ax, plus bx squared plus 15b. The order you write these is yours. I just put the 15 in front of the b, but you do exactly what you want to do. There's nothing sacred about what I'm writing here. I think I'm just a creature of habit. And then of course we have plus cx plus d. Now notice here, we don't have as simple of equations as we had before. We've got 4 coefficients. So we may have to go ahead and create some equations that have 2 of the coefficients in them. And then as we determine another one of those coefficients, we can go back to that equation. So that will help us move the problem forward. So first, let's just do x equals 0. See what that gives us. So when x is 0, we just get a 15 on the left-hand side. So we get 0, 0, 0, 0. We get a 15b plus a d. 15b plus a d. So if we can find d or b, we have the other one. So that's not as clean as we had before, but it's certainly a step forward. Now, what's the lazy thing to do? Differentiate, which we do, and then we'll try to develop some more equations. Differentiate. Okay, so we get 2x plus 1 plus 0, 3ax squared plus 15a plus 2bx 0 plus c 0. Okay, x equals 0. So what's this going to give us? 1 equals 0, 0, 15a plus c. So we're thinking, okay, well, good, easy, differentiate again. I bet you never thought you'd be differentiating to find coefficients. So differentiate 2, 0, 6ax 0 plus 2b. Now let x equal 0. X equals 0. So we get 2b equals 2, so b is 1. So the deal here is once you keep differentiating, if you substitute 0 and there's only one coefficient left, then you're good to go. Now, look, we've got a b here, so we can find d. So then d equals 15 minus 15b. But b is 1, so we get 15 minus 15 equals 0. So d is 0. Now, so what do we have left? Let's see here. We've got b, and now we need to find c. I lost my share. Sorry. Every time I touch my computer, sometimes it does some strange things. Where it go? So now, everybody look at this. If we go back through everything and we look at what we have and what we don't have, notice the very last equation here. Look right here. Look right here. Let's differentiate again. Differentiate. We're kind of at the last bit here. So this will be 0 equals 6a. 0 equals 6a. So a is 0. Then, now we got a is 0, so c equals 1. Yeah, I set papers on my laptop, and then sometimes they do some strange things. Now, if we look at this, let me just go back and summarize everything we've done here. And this is very important. We started out with fairly complicated equation, but very simple. Set x equal to 0, get this equation. Differentiate x equals 0, get this equation. Differentiate x equals 0 gives us b. Go back to this equation, get d, then differentiate again. A is 0. Go back to this equation, c is 1. That's the quickest way to do it. You will not be able to do this any quicker if you choose other methods. So we have A, let's summarize, A equals 0, B equals 1, C equals 1, D equals 0. Okay. The first time I did this in class, they said, "That's magic, Professor Ron." I said, "It is, but it's a legitimate technique and rarely taught, rarely taught." So now let's finish. So let me get another sheet of paper here. So let's go back. Let's take what we have here and fill in our integral. So we have our integral right now will be the integral. Let's go ahead and write it down. X squared plus x plus 15 x to the 4th plus 30x squared plus 225 dx. And so now, notice here, we have A is 0, so we have B, so we have 1 over x squared plus 15. And then the last one, we just get x over x squared plus 15 squared because D is 0. Now look at this. The first one is easy. That's just an arctangent. Now notice, remember the thing is when we write down our decomposition, we go right back to this and we substitute. B is 1, C is 1, A and D are 0. So there's our new integral equation embedded in this. So now this is just inverse tangent. And then, of course, this is a du over u. Well, no, just to add 1 divided by the new power. Let me refocus. So look here, this is inverse tangent. A is going to be square root of 15. And here, let's go ahead and rewrite these. So we've got, let me do this. All right, A equals square root 15. So I'll just do it. I'll do it like this, just to remind you of where you've been. Right there. And then, of course, here we've got a u. U equals 2. Let me not differentiate first. U equals x squared plus 15. Du, excuse me, equals 2x dx. So we're going to add 1 divided by the new power. So this will be plus 1/2 x squared plus 15 to the negative 2, 2x dx. So now these are ready to go. Now this is, well, let me just say here, easy and standard form. That's the inverse tangent from back at the beginning. So we have 1 over a, so 1 over the square root of 15, inverse tangent, x over square root 15. The beauty of the inverse tangent, these inverse trig forms that we had at the very first, is that they are so nice and provide great antiderivatives with little or no effort because we mastered them. And then add 1 divided by the new power. So we have plus 1/2. The new power is -1, so we have a negative. And then this gives us x squared plus 15 to the -1 plus a c. So we can clean that up a little bit. So 1 over square root of 15, inverse tangent, x over the square root of 15. Then we have minus. So just bring everything downstairs, I guess, 2x squared plus 15. That is a very elegant problem and done with partial fraction decomposition. So again, when you have distinct linear factors, easy. Just pick simple values that clear out one term and solve for the remaining. That's easy. That is not a problem. When you have irreducible quadratics, try your x equals 0. Notice what I'm doing here with this. In the past, I've used any number, but I feel that the differentiation technique is so easy, then that means you can use 0 again, and then you don't have to use all of these other numbers which require extra arithmetic. So as I teach and I find certain ways that are easier for students, I tend to push those forward. When I did a lot of honor sections, I had my students spend a lot of time just deriving formulas in the integral table. They would spend hours in the honors lounge doing that, and that was fine. But I always told them, I said, you know, make sure that you're utilizing techniques that make your processes efficient. But they were very keen on getting a correct formula, so I couldn't argue with that. But when it comes to doing this kind of problem, just remember, you always have at your disposal the ability to differentiate, to reduce new equation x equals 0 and get very simple algebraic restrictions that are easily solved. So that's a fun technique. I think the trig sub is fun, but it seems to be a little bit winded at times. The partial fraction decomposition, for the most part, is simple and doesn't require any grand knowledge of trig unless you just get a trig set up. So I don't want to say, oh, it's always easy, because then I'll do a problem and you're thinking, well, that wasn't so simple, Professor Ron. So now what I want to do is look at an example from your WebAssign that uses a substitution. Yeah, this will be a good one. So let's try this one. So this will remind you what you did in Cal 1. Don't forget integration by parts. You know, that's our friend too. X minus 36. Now, what I want you to do, I want you to go back to the very beginning and have that formula ready, our formulas that we derived, because I think we're looking at this problem, I think we're going to be able to use it. Now, in this case, remember, the partial fraction decomposition technique works with rational expressions, so we can't really work it too well with radicals. So with this kind of problem, if we transform this to a problem that has rationals only, that is ratio of two polynomials, we can apply the decomposition technique. So here's the trick, of course. We'll let the u be the square root of x. So of course, u squared is x. Now this is the technique from Cal 1, the miscellaneous substitution, and it's very powerful, as you well know. So now we get what? 2u du, equals dx. And now, if you will, this is, we got downstairs, we just got x minus 36 will be u squared minus 36. So we're good to go. So let's write it out. Now remember, I did that, the definite integral, because those get a little bit complicated, but Again, you all are pretty good at arithmetic. I mean, need to make sure you got these techniques down. So we get u for square root of x, and then of course u is, excuse me, x is u squared, so we get u squared minus 36. And then of course, dx is 2u du. So we get 2u squared du over u squared minus 36. Now, this is where you think about the fact that when you divide, in this case, you're going to get a 2. And then when you multiply, you're going to get, I'll just do it out, but you can actually do this in your head, but don't do that. But I won't do it. I'll write it out. But you can do these in your head, 2u squared. So you're going to get a 2 clearly. So that gives you a 2u squared. And then you have what, minus 2. So this is going to be a 72. So you just basically say 2 times the 36, and then you get the plus, and you've got what you need. But sometimes that's a little bit hard to see early in the morning. So this will just give you 2 plus 72 over u squared minus 36. I had a professor at A&M that differential geometry, she could do partial derivatives in her head, and we scrambled to catch up with her, but it was what it was, and it was a great course. But boy, she found her love in differential geometry. So now you look at this and say, okay, good deal, right here, right there, right there. We don't have to reinvent the wheel because we've already done this. So I'll write this in red. When you're doing your quizzes and all, you can certainly use your formulas that we derived. So recall du over u squared minus a squared is 1 over 2a ln a minus u over a plus u plus a constant. So that was what we derived when we first started the partial fractions, and that's all we have. So you don't, what I'm trying to say, ladies and gentlemen, is that don't go, you're on a test, do not redo this with partial fraction decomposition. I mean, that's a common integral that comes up all the time, and so just go ahead and work it, leave it alone. I mean, you can work through it, but if you've got this, then you're good to go. So now what does that give us? So we'll get 2u, right, that easy integral, 2u. Then we have plus, now, of course, this is table ready. I mean, my goodness, we got the 72 hanging out, but that's all. So let me just kind of factor that. So this, we've got this, so boom, we go here, but we got the 72, which we factor, and then we have 1 over 2a. So here, a equals 6. So we have 2 times 6. And then we have ln, and then a, 6 minus u, 6 plus u. See, I teach you how to use the integral table before you actually get to it, and then it turns out to be a blessing. So now, so we have, let's just 2u, well, u is square root, 2 square root x. And so we have here, we've got a 36 divided by 6, which is 6. And then we have 6 minus square root x, 6 plus square root x plus a constant. Now, of course, if you want to flip these around, x squared minus 6, and those that you can, it doesn't matter. There's just absolute value, so it won't make any difference. Your choice. Lots of students like to do the square root of x first, but it's absolute value, so it won't change anything. But this is exactly what you need right here. So the beauty of this problem is that it looks like a Cal 1 problem, and it pretty much is, except when you get to that. And that's when you're like, okay, but that's Pythagorean. So you're going to get this nice symmetry going on. So you could use, your trig sub, but that's, this makes a great way to introduce the partial fraction decomposition. And plus, we have this formula. We've already derived it. We're good to go. We can use it. And I'll say this, as you get more and more adept, as you take your engineering classes and your physics classes, your professors will say, okay, here's a partial integral table, use it. And you should use it. And the nice part about this is that this one was ready to go. This was like, how much more user-friendly can we get than that? That's just easy. And again, with absolute values, you have a lot of flexibility here, but don't change anything if you're not competent. Just use what you know. Okay, now I want to introduce one other example that I have here. And then there's a nice problem at the end of the section, and I want to help you set it up, but then I want you to work on it. It's a volume computation, and you actually end up with an integral that turns out to be really, really, really simple. The way it's set up, you can actually use the disk method. So this next example, we're going to actually talk about Weierstrass technique when we've got complicated rational expressions of sine and cosine, ladies and gentlemen, but we're only going to use that when we have to. I mean, let's face it, you look at some of these computer algebra systems that are free online, and they use, I don't know, I know you all use them. I mean, I'm not a foolish person, but the thing is that some of the techniques that are utilized are not what I've taught you, and they utilize substitutions that probably don't even make any sense to you. So what we try to do in Calculus 2 is give you a algorithm that utilizes what you know, and a lot of the computer algebra systems will just be coded in such a way that they'll use what works, not necessarily what you have to do or what would be actually much easier. But with that said, that's the nature of computers. So let's look at this example. We have cosine x, and we have sine x. Yeah, I remember when I used to teach the kids Maple when I was a graduate student at Texas A&M. I'd always know when they were using the Maple to do their homework. I said, kids, you all don't even know what you're doing. I said, you just written these things down. They said, oh, Professor Ron, that's not right. And then they just called me Ron because I wasn't a professor then. But I just said, okay, well, just remember, on your test, you use pencil and paper. They had a lot harder than you all do. Back in the day when I was in grad school, they had a pencil and a piece of paper, and that was it. So the technology has made things a little bit easier. So now when we look at this, we think, okay, well, it's like the last problem. We don't have U's and X's, but we have a setup that we can actually try to think of that might give us something that will work. So now let's just do what we did before with the square root of X. Notice this will factor. If we let the sine be replaced by U, we're going to get two linear factors. So here, U is sine X. Of course, notice we have a rational expression of sines and cosines, but we see that we think the partial fraction decomposition will bail us out. So now du is just cosine x dx. Well, lo and behold, so now let's see that we got everything we need. Let's do it. So we got what? Let me write this way. Cosine x dx is du. And then we have u plus u squared. So now we can factor du u times u plus 1. Now, again, this is not nice and elegant with a Pythagorean denominator, but these are what? Distinct linear. Distinct. This is so easy now, after doing all those irreducible quadratics, this is a walk in the park. Distinct linear. So what we do, just like we did in the last problem, is we transform this to a rational expression, and then we can apply the decomposition to the rational expression. So let's do it. So we have 1 over u times u plus 1. And again, because these are distinct linear factors, we'll just have an a and a b. So we have a over u plus b over u plus 1. And now, just like we did before, we want to clear the denominators. So we multiply through by u times u plus 1. That'll absorb the u times u plus 1 on the left-hand side to give us 1. And then we get a times u plus 1 plus b times u. Now again, like I say, we can just choose easy values for u and be done. So again, we have an equation that is true for all values u. That's the beauty of this. This is basically the Oliver Heaviside cover-up method. But I don't do the cover-up like he does. I just go ahead and go to this. Dr. Larson always pushes for this equation, and I agree with it because it allows you to do the differentiation technique, which I've been doing in the class, which again, very simple. So u equals -1. So we get 1. This absorbs. We have b times -1. So b is what? -1. Sometimes this technique is so easy that you can just say things that aren't true. Just be very careful as you use it. And then, of course, u equals 0 will annihilate this term and give us this. So we have 1 equals a, 0 plus 1 is 1. So a is 1. So what I like to do is, once we've done the quadratics, the irreducible quadratics, go back to these simpler problems with just basic substitution. So now you can combine some earlier techniques that you would think about with miscellaneous substitution with the fractional decomposition, and then arrive at an antiderivative. So now let's go back to our identity right here. So this says the integral cosine x sine x plus sine squared dx. So now this will give us, we'll get the integral 1 over u plus -1 over u plus 1, use the identity, du. Now, like I said before, these integrals are so easy, we don't even have to think about it. So they're both table ready, right? We have the u and the u plus 1. So we get natural log of the absolute value of u minus natural log absolute value of u plus 1. But the key here is always utilizing what you know. Use what you know to move the problem forward. Don't make it up. Do not make it up. There's no need to make up anything. You will never need to make up something. I will give you problems that you can solve. And so now we just replace the u with the sine x. So this will be, if you want, go ahead and combine with the difference rule. What is it? The log, difference of two logs is the log of a quotient. do this, the difference rule, right? The difference rule. So we have natural log, and then we've got sine x, and then sine x plus 1. So that's a very elegant rendering of a problem that, again, utilizes a very simple technique. Now you're professionals pretty much. You can differentiate to find coefficients when you've got irreducible quadratics. You can use easy values of u whenever you want. After you differentiate, you use 0 again. Why? Because 0 is easy. So again, I want the partial fraction decomposition to just be an additional technique that makes what you already do better, in the sense that now you can deal with rational expressions, just like, remember in pre-cal, you could do all those nice graphs, and then you got the calculus and you figured out that all of that you did in pre-cal was actually correct. I mean, that was pretty neat. And so now the rational functions are coming back, but as we move through and you move into other classes, you will hit some other integrals which will not be as friendly. And those are the elliptic integrals, which are volumes have been written on those. And that's always a good source of research. They are a good way to keep your mind sharp when you want to get back into the routine. So now what I wanted to do is just give you the heads up on a problem here. When you actually compute, I want to go ahead and set it up for you, and I want you to finish it. Here, I had another problem. I was working below it, so I trimmed it off, and I want to share this with you. This is one of your WebAssign problems, and I just want to help you set it up. The problem comes to you in a very interesting way. You're given this like the equation of a circle. That is, you have this curve which is symmetric, a nice even function for x between 0 and 1, and you want to revolve the region about the x-axis. Well, the thing is that you think of this just like arcs of a circle. So you have y is plus or minus the square root of this to get the upper arc and the lower arc, so to speak. So that'll give you plus or minus the absolute value of 4 minus x divided by x plus 1. And then, of course, removing the absolute values, because, of course, x lives here, that just gives you plus or minus the fraction. Now, of course, with this, you have the reflection of this curve in the x-axis. So you've got a curve going like this and then a curve that's reflected. So by symmetry, you can let your r, that is, this abuts the x-axis. You want to actually revolve this region about the x-axis, but you just take the symmetry and let your big R just be 4 minus x divided by x plus 1. So this is what we call the disk method. I thought this was an interesting problem, and not a simple problem when you think about the analysis. I wrote analysis here. So now, in order to complete the problem, we use the disk method. So you're going to get pi times r squared from 0 to 1 dx. And when you multiply this out, you're going to get what? 16 minus 8x plus x squared. And then you've got 1 plus x quantity squared in the denominator. Now, here's the thing about this problem. What you see, and this is talking about techniques I've already shared with you, you have the degrees are the same. The degrees are the same, so you need to multiply this out and divide. And the beauty of this problem is that you end up with very simple integrals here. But this is where you're going to have to do some rigging, and I'll talk about this more as we go through other examples. But the idea is that at this point you rig, and you actually end up with two easy integrals here. One, divide the power rule, add 1, divide by the new power, and then of course this is just a du over u interval. The beauty of this particular problem, and when I thought about including this in my lecture, is that it focuses on division to reduce to a simple quotient and then a fraction, which you now rig in order to get your du over u and your inverse trig function integral. And then everything works out very nicely. But what I wanted to focus on here is that the setup has to do with this, utilizing the symmetry and using the disk method. So that should give you a way to actually work out this problem without too much difficulty. Again, a very nice problem. And I included it. I'm not really sure why I did, but it seems to be a really nice problem and something that you can do. Now, we will not have lecture on Wednesday, but of course you will be completing your test between Thursday and Saturday. And then of course you will have your homework due. I've kind of shifted everything up to Tuesday and Wednesday to give you a little extra time on your quizzes and your homework. And I think that works well for everybody. Even my pre-cal students seem to like it. And again, I just want to keep you on track. And then of course you'll have your partial fractions and your trig sub due then. And then for the rest of chapter 8, we're going to talk about some Weierstrass substitution and then some improper integrals. The improper integrals aren't things that we spend a whole lot of time with, but they do come up, so we need to be familiar with them when we do the integral test with infinite series. So again, on Wednesday, take the time to get some rest, sleep in, relax a little bit. Go ahead and decide on a good time to take your test number 2. Remember, you have the flexibility of the window, and you choose a time which will work best for you. There are no excuses, and I expect you to get the test completed in the window that I've given you. Remember, my goal for you is to have success, but that success comes with a lot of hard work. And so I will remind you that you need to work through the lectures, you need to work through the lecture notes, you need to work through the PowerPoints and the old test to make sure you have your skill set where it needs to be. I am thoroughly checking WebAssign, and I'm very aware of your login information. And in some cases, there are some discrepancies, which I may have to consider talking to you about. Ladies and gentlemen, I demand that my students be honest. And any lack of that would have very severe consequences. So make sure that you are doing your work with integrity and that you're doing your work in an honest manner, because that's exactly what I expect of you as a San Jacinto College student. Okay, so listen, thank you very much for your attendance today. I wish you well as you prepare for your test. Everybody have a good day and enjoy the lack of rain. Bye.